Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the metal casting. In this particular presentation, I'll be focusing on enhancing the performance of casting by controlling the microstructure. So, one of the very important approach of controlling or adjusting the microstructure is the heat treatment. Heat treatment allows us to change the grain structure or change the phase structure also. So we can adjust the size of the grain, shape of the grain, or we can also regulate or control the phases as per the requirement of the properties. So in this particular presentation, I'll be talking about the heat treatments related with the precipitation hardenable aluminum alloys and the heat treatment of the ferrous metals, particularly steels. So as far as content is concerned, we'll be talking about the heat treatment of castings. So heat treatment involves basically one is done for stress relieving heat treatment, which is done for stress relieving. The second is the heat treatment for the aluminum alloys. Okay, so here we'll be talking about the two types of the heat treatment, T6 and T4 heat treatment, and then also heat treatment of the transformation hardenable alloys, particularly steels. So, like heat treatment like annealing, normalizing, hardening, coupled with the tempering. Okay, so these are the kind of heat treatments about which we will be talking. In the main purpose of the heat treatment, if we see, when heating of the casting is done, then what it does basically it softens the metal. Okay, softening of the metal, what it leads to the relaxing the relaxing of or relaxation of the locked in strain, and once the locked in strain in the casting is relieved or it is relaxed, then our residual stresses are relieved or they are minimized. Therefore, if the casting is heated to the higher temperature, softening leading to the reduced residual stresses, and once this happens, then the distortion tendency of casting is minimized, especially during the machining. Also the cracking tendency is minimized later on. Okay, so it is important that stresses are relaxed or relieved. For this, we perform the heating of the casting to a temperature below the critical temperature above which phase change can take place. So this critical temperature should be lesser than the temperature at which the changes of the phase is possible, because we just want to soften, we don't want to make much of the changes in the phase structure of the casting, because otherwise it can alter the properties significantly. As far as the other type of the heat treatment is concerned, especially this is true for your aluminum alloys, precipitation hardenable aluminum alloys, like which are like aluminum, copper, magnesium type, or aluminum, silicon, magnesium, copper type, or aluminum, magnesium, silicon type, or say we have the aluminum, zinc, magnesium. Okay, these are considered the precipitation hardenable aluminum alloys. Aluminum casting Aluminum castings are mostly made of the aluminum silicon alloys coupled with the little percentage of the magnesium and copper. Okay, and also sometimes nickel for the high temperature properties. So when these alloying elements are there, then they also allow the precipitation hardening during the heat treatment, means during the heat treatment of the castings, by forming the precipitation hardening precipitates in the casting to enhance the strength and hardness. Okay, that is true for the pH alloy. So what we do, we can perform T6 heat treatment, that is called, this is a combination of the solutionizing, quenching and artificial aging. Okay, these are three steps. But in case of the T4 heat treatment, what we do, solutionizing, quenching, followed by natural aging. There is no artificial aging, but aging is done under the ambient condition. So this happens slowly. Okay, so these are the steps related to the two types of the heat treatment. But as far as, so in this case, we try to develop the fine precipitates of say Mg2Si, Al2Cu, Mg2Zn. So these are the kind of the precipitates which we like to develop during the precipitation hardening treatments, and fine well distributed precipitates in aluminum alloys help in enhancing the strength of the castings. Okay, as far as the heat treatment of the transformation hardenable metal is concerned, like steels, so this is based on the two approaches. One, either it will allow just this change in the grain structure, like in normalizing or in annealing. So in annealing, basically the coarse perlite is produced, and in normalizing, we get the fine perlite. But as far as the hardening and tempering is concerned, quenching and tempering is concerned, we try to change the soft phases into the hard phases. Okay, so that you see our ferrite and perlite is transformed into the martensite, and thereafter to induce reasonably good degree of the toughness and ductility, the tempering is performed. Also, the residual stresses are relieved. This is the main approach as well as the objective of controlling the structure and properties. So, what are the different purposes which are realized through the heat treatment of castings? Okay, so the we can get the stress relieving. Stresses can get relieved, so that reduces the distortion tendency during the machining, reduces the cracking tendency, as well as it also helps in improving the mechanical performance of the castings, because whenever the residual stresses are present, they negatively impact the mechanical performance, especially fatigue resistance and the tensile strength of the casting. Dimensional stability is also enhanced because the stresses, residual stresses are relieved, and subsequently during the machining, there is no the change in dimensions and the major shape of the casting during the due to the distortion. Okay, and reduced distortion tendency. This is happening primarily due to the reduced residual stresses. Okay, the major purpose of the heat treatment is to control the microstructure. So uh, we can change the grain structure of the casting, or we can change the phase structure, or both. Okay, and when this controlled change in the structure is realized, we are able to attain the desired set of the mechanical properties. There can be multiple purposes, like it may be like increasing the hardness or reducing the hardness, increasing the yield strength or reducing the yield strength, or improving the machining behavior. Okay, improving the strength and toughness. So depending upon the kind of properties desired from a casting, the suitable control over the microstructure is realized for attaining the desired set of the mechanical properties. So, as far as the stress relieving is concerned, this is one of the approach where the casting is heating of casting to high temperature enough so that the yield strength or the flow stress of the metal is reduced. Okay, so that the locked in strain is relaxed. Okay, so higher the temperature, greater will be the reduction in yield strength, greater will be the reduction in the relaxation in the locked in strain, and that in turn will help in reducing the residual stresses. So if we see, say in case of the ferrous metal castings, if we go for the stress relieving at the higher temperature, then the extent of stress relaxation is increasing. At low temperature, stress relaxation is very less, but at the higher temperature, if we see at 600, the stress relaxation is 70 to 80 or 90% of the residual stresses which were present in the beginning. So this is one aspect. Why it is happening? Because increasing the temperature of casting is reducing the flow stress or yield strength. That in turn is helping to reduce the locked in strain, and which in turn help in reducing the residual stresses. Okay, this is one aspect. So the temperature is one thing and the time is another. If we heat the castings at a higher temperature for a stress relieving for longer time, then we get the longer or more relaxation. So at low for shorter time, the stress relaxation is somewhat less as compared to that for the longer time. So for any temperature, if we see longer temperature or longer heating of the casting for longer time will be causing the greater relaxation as compared to that for the shorter time of the relaxation. So stress relieving, this heating is one of the approach which is used for reducing the residual stresses. So heating reduces the flow stresses that in turn help in relaxing the locked in strain, and the temperature is one of the major factors because it directly affects the yield strength in relaxing the locked in strain. Time also affects, but in minor way, to the in relieving the residual stresses. If the heating is not possible, and still if you want the stress relaxation of the residual stresses, then another mechanical method that can be used is the short peening. So in the short peening, steel balls are accelerated to the high speed, then these are directed over the surface of the casting. So if the strain is locked in at the surfaces, then due to the controlled surface layer deformation, the locked in strain is relieved, and it helps in developing the compressive residual stresses at the surface, and that in turn helps in improving the tensile strength as well as the fatigue strength or fatigue resistance of the casting. So short pinning also relieves the residual stresses, and at the same time it helps in developing the compressive residual stresses at the surface, which is considered to be favorable for improving the performance of the casting. If you focus on the different kind of the heat treatments which are performed on the cast aluminum silicon alloys, okay, so in USA and in say England, so the kind of the grades which are allotted, these are very common grades which are used in India also, like the kind and which is this the type of the heat treatment is the kind of temper condition of the aluminum casting. If we try to learn in that way, cast aluminum alloys is aluminum casting in as cast condition is designated as F grade, okay, and the aluminum casting in annealed condition without any mechanical, just heating is done at a higher temperature, so this is designated as O grade, okay. Then if the casting is subjected to the controlled cooling after the solidification followed by natural aging, then this is assigned as a T1 grade. And if the casting is heat solution treated followed by natural aging, it is assigned as a T4 grade. Okay. If the casting is subjected to the controlled cooling after the solidification followed by artificial aging or artificial aging or over aging, it is designed as it is designated as a T5 temper condition. If the casting is subject to the solution treatment followed by artificial aging, then it is given as a T6 treatment, okay. And then casting is subjected to the solution treatment followed by artificial underaging, then it is given as a T64 treatment. And casting subject to the solution treatment followed by artificial overaging, then it is given as a T7 temper condition, okay. So these are the different that heat treatment conditions or the temper conditions when the castings are subjected to the variety of the heat treatment approaches, okay. The typical heat treatment conditions which are used for improving the microstructure and properties of the precipitation hardenable aluminum alloys are given in this table. What it shows, like LM24 subjected to the T60 treatment, LM25 subjected to the T5E treatment, and LM25 subjected to the T6E treatment. So this table shows the different time values for which solutionizing is to be done at the given temperatures, followed by the quenching in water to realize the supersaturated solid solution. And thereafter, the artificial aging is carried out at these different temperatures for the different times. Okay, the typical compositions of the LM25 and the LM4 is given here in this slide. The heat treatment cycle, which is used for improving the structure and properties of precipitation hardenable aluminum alloys, is this, like where the first step is to heat up to the desired solutionizing temperature, and this will be so this temperature and time certainly will depend upon the type of the alloy and its condition, whether it is forged, cast, or which condition of the alloy is. And then it is quenched rapidly to realize the supersaturated solid solution, so that later on we can get the development of the precipitates during the either not natural aging or artificial aging. So for artificial aging, we have to reheat it up the say 150 to 200 or 220 degrees centigrade. And once the precipitation is over, then so there are three stages in pH alloys: solutionizing, quenching, and artificial aging. Okay, so the time and temperature of the each stage is important for developing the desired microstructure. Solutionizing temperature significantly affects the microstructure and mechanical properties, because what we want first, the homogeneous solid solution of the alloys is developed. And for that, everything, whether it is intermetallic compound, the precipitates, or alloying elements, everything should get dissolved in the aluminum matrix, and therefore solutionizing is done. Selection of the suitable solutionizing temperature is crucial, so that it can form the solid solution of the solutes such as Mg, Cu, Si, and zinc in aluminum matrix. And for that, alloys are heated to the temperature high enough above the solvus line, so that the everything gets dissolved and homogeneous solid solution is formed. This temperature is below the liquidus temperature, certainly, because during the heat treatment we don't want any kind of the melting. During the solutionizing, the precipitates and the compounds will be decomposing, and they will be diffusing to form the homogeneous solid solution. The temperature and time both affects the homogeneity and the kind of the solutionizing that will be done, that will be happening. So higher temperature for longer time, if maintained, it promotes the homogenization of the solid solution that will be formed. Okay, so if we go for the higher solutionizing temperature, it will be resulting in the more effective homogenization, followed by the quenching and the artificial aging, and this in turn will be increasing the hardness, and this is attributed to the improved solutionizing, resulting in the improved precipitation in the later stages. The soaking time for solutionizing is also important, because not just the temperature but also time is crucial for development of the homogeneous solid solution. Time required for solution temperature depends on the alloy composition. Certainly, if there are few alloying elements or many alloying elements forming the complex compounds and intermetallics, then they will be taking longer time. Casting procedures, like the sand cast alloys, will be resulting in the coarse grain structure, coarse compounds, and they will be taking longer time to get dissolved and form the homogeneous solid solutions, as compared to those developed using the die casting or forming and forging based processes. Solutionizing temperature certainly affects the soaking time, because higher temperature accelerates the decomposition and diffusion, and therefore it reduces the soaking time for development of the homogeneous solid solution. Because all these parameters like alloy composition, casting procedure, solutionizing, section thickness, etc., affect the microstructure, and therefore these affect the soaking time. Greater is the section thickness of casting, greater will be the time it will be taking for development of the homogeneous solid solution. Quenching temperature is crucial. Quenching temperature and cooling rate both are crucial for realizing the supersaturated solid solution after development of the homogeneous solid solution. So the alloy which is in homogeneous solid solution is stayed when quenched at low temperature rapidly, then it forms the supersaturated solid solution. Okay, so this supersaturated solid solution, when given the exposure at either at a higher temperature or a room temperature, it allows the formation of the precipitate, and that in turn affects the mechanical properties. So it is important to form a supersaturated solid solution, and that is realized through the quenching step. Dependence of the mechanical properties of cast aluminum alloys after solutionizing on cooling rate is known as quench sensitivity. Okay, the maximum value of hardness after aging has been found as a function of the has been found to be affected by the cooling rate, especially at the lower cooling rates. Okay, when the cooling rate is low, then the effect is more significant with the increase of the cooling rate. Okay, cooling rate in temperature range of 200 to 450 degrees centigrade is crucial. So when we are cooling from the solutionizing temperature, say 500, 550, 520 degrees centigrade, so the cooling rate, which is given especially in the temperature range of 450 to 200 degrees centigrade, that is critical in determining the end structure and the mechanical properties of the alloys. So this is what we can see here. Increasing the cooling rate increases the hardness, and this is what indicates the quench sensitivity. Okay. And this is what also we can say that after solutionizing, when we cool at a different rates and given the different kind of the aging time for precipitation hardening. So the low cooling rate offers the lower hardness as compared to that of the conditions when higher cooling rates are used, because higher cooling rates allow the better development of the supersaturated solid solution or realizing the development of precipitates in the later stages. Now we will see like the effect of heat treatment on the microstructure. So in as cast structure of the aluminum alloy, we can see here he's having the aluminum dendrites and the eutectic of the aluminum silicon in the matrix. But when we provide the T6 heat treatment, then the cast structure is completely destroyed, and what we get the very fine, well distributed eutectic silicon. Okay, and this is what it shows like the cast structure is completely destroyed in case of the aluminum silicon alloys when they are subjected to the T6 heat treatment. The very refined spheroidized eutectic silicon is found in the aluminum matrix. Okay, and if we see the effect of the aging time on the yield strength, which is realized on aging at different temperatures. So what we see, if we do the aging at lower temperatures, then it takes longer aging time to realize the maximum yield strength. Okay, then on increasing the aging temperature reduces the time required to attain the peak strength. Okay, similarly, if we see the aging time required for peak yield strength at the different aging temperatures, if solidification time is increased, then it takes longer time to realize the maximum strength at different temperatures. Say at 260 degrees centigrade aging temperature, the aging time required for maximum yield strength is increasing. So the same trend is observed at the different temperatures. Okay, and another thing that we can see, increasing the temperature reduces the time required to attain the peak yield strength. That's what we can see here in the aging time. When aging is done, during the aging, the supersaturated solid solution tends to form the fine precipitates. Say in case of the aluminum, depending upon the composition, in aluminum magnesium silicon alloys, it will be Mg2Si which will be formed. In case of the aluminum copper alloys, it is CuAl2 which is formed. And if nickel is there, then it will be forming the NiAl3 kind of the precipitates. And these precipitates actually, when these are well distributed in the aluminum matrix, they effectively act as a barrier for the movement of dislocations, which in turn increases the hardness and yield strength. Okay, so this is what we can see on increasing the aging time. What we can see, we attain the maximum strength at particular value. Thereafter, strength starts decreasing. This is what is termed as the over aging. Okay, and the proportion of the hardening precipitates like Mg2Si, when it is increased, then it increases the yield strength as well as the ultimate strength. The delay period is the another thing like in industries, what we find most of the time that it is not possible to do the aging immediately after the quenching. So the time gap between the end of the quenching and beginning of the artificial aging is termed as the delay period. So in actual practice, delay period is unavoidable due to the number of limitations which are encountered in the industry, such as furnace breakdown, availability of the power, or inadequate furnace capacity. That is why, and when there is a delay, it leads to the cluster formation of the solute in the matrix, which reduces the supersaturation, and that in turn adversely affects the precipitates, or the amount of the precipitate, size of the precipitates that will be formed. The size of the clusters increases with the delay time. Clustering and coarsening of the solute precipitates has been attributed to the effect of the delayed aging on the mechanical properties. So, what is the best way to reduce the negative effect of the delay period on the structure and property? The after quenching, the alloy should be stored at a lower temperature so that unnecessary the clustering of the solute is avoided. And also, it has been reported like addition of the Mg and the copper and cadmium reduces the effect of the delay period. That's what we can see here. Addition of the magnesium reduces the kind of the drop that is happening due to the delay. Okay, and similarly we can see cadmium, indium, and copper. The increase in the hardness. See, addition certainly increases, addition of these elements increases the hardness, but the effect of the delay is somewhat reduced. So now I'll summarize this presentation. In this presentation, basically I've talked about the heat treatment, which is typically used for the precipitation hardening aluminum alloys, involving the solutionizing, quenching, and how these heat treatments affect the microstructure and mechanical properties. Thank you for your attention.